Thank you to all for attending this presentation. Uh, it's, uh, it's, it's a contrast to what Saurav presented this morning. He talked a lot about precast construction, so by chance I decided to talk all about cast in place and kind of the circumstances where you need to where you have the situation where bridges are built higher and lowered in place. So my presentation will cover the following topics. I'll give you a brief history of the cast-in-place post-tension box girder bridge construction, the methods that are used in the construction of these bridges, including soffit fill and false work. Slowly, soffit fill construction has kind of gone with the traffic volumes increasing. Most of the bridges are now constructed with false work. So I'll provide some information about how to build these bridges over live traffic when false work is required to build these structures, the clearance requirements of the bridges while during new construction or widening, and what are the circumstances under which the bridges are built higher and lowered in place. I will also show a project highlight on the SR 101 Frank Lloyd Wright Boulevard Bridge in Arizona. And this is a project that I worked on when I was at WSP, and I see a lot of my former colleagues here, so it's kind of a good opportunity for me to show them what I was doing in my night shift. And I'll present the original design, which had a precast box spliced girder and how it was value engineered, and the bridge was redesigned in 4 months to go to cast in place post tension box girder with lowering required. I will share some of the design and details that we used in the VE, along with the construction submittals that go into the project, and finally I will share the construction photos and videos from the progress on the bridge. So what exactly is a cast-in-place post-tension box girder bridge? It's kind of a mouthful to even say it, but it's a type of construction that requires the concrete to be in the final position in place when it's poured, and the post-tensioning just means that the pre-stress is applied after the concrete pours occur, as contrast to pre-tensioning, which is used in precast, where the strands are tensioned before the concrete is poured. The box girder essentially just is the description of the shape of these structures, which is in the shape of the box, and the sloped webs provided a good aesthetic quality. On the right here is a quick overview of how these bridges are constructed. So the first step is to construct the false work and then build the webs and the bottom soffit slab. Then you pour the deck, and you then post tension the bridge and remove the false work. Sorry about that. I don't know why. So Caltrans basically pioneered this type of construction throughout the 1960s through about even to the current day. They build most of their bridges with cast-in-place post-tension box bridges. The typical spans are about 250 feet to 300 foot max, which kind of falls outside the range of the precast girders. And in case of system interchanges, they use a hinge that is shown in the red circle here. It's called a hinge, and we're able to increase the length of individual bridges using these hinges, which allow for rotation and thermal movement. So the neighboring states like Arizona, Colorado, Nevada, and Washington have also adopted this type of construction quite extensively in their freeway system. Even in North Texas, we do have a couple of such examples. When you drive on US 75 at Coit, you have those two braided ramps that are cast in place post tension. As you can see, and the US 75 at Highway 12 as well. The column connection in these bridges are different than what is shown traditionally in the Western United States, where you have a more integral connection. Another example of this type of bridge in North Texas is the UT Southwest overhead connector, which I was fortunate enough to be able to locate the picture of the bridge under construction. As you can see, it's constructed over an extensive array of false work, and this is the current picture of the bridge. So what exactly are these types of bridges? They're a subset of segmental construction, if you will, where the segments are poured continuous. And you know, this bridge type has proven to be cost effective and span longer than precast eye girders. And even in the latest cost information that Caltrans publishes, these bridges have are pretty comparative cost as far as cost per square foot. I just showed a couple of examples of the precast segmental just to show you the contrast between the cast in place and the precast segmental construction, where you have individual segments that are erected side by side, you know, like a span by span or a balanced cantilever approach, instead of pouring it continuous. And there are some examples where even the precast segmental bridge has been constructed using false work, like the I-59, I-20 interchange in Alabama, where they were able to close the freeway down for a whole year. And so they were able to build segmental construction with false work. In the old days, when room was available, bridges that were cast in place were built with soffit fill. So essentially the fill was built up in place, and the bridge was poured on top of that engineered fill, and then the fill excavated underneath to make room for the freeway, like shown in this picture. But however, with the traffic volumes increasing and basically no you know, room available anymore with urbanization, most of the cast in place construction now has to happen with false work. So this is a picture of a two-span structure that is, the bottom picture shows the existing bridge that is being prepared for widening. And then you see the picture at the top, the same bridge, it's being widened on the side, and you can see the false work construction. The false work is essentially a system of steel and wood members that are framed together that carry the load of the bridge temporarily during construction till the concrete is poured and the post tensioning is applied. So what are the requirements of building bridges on false work? Obviously, you have to have adequate vertical clearance under the false work to allow for traffic, and the Arizona DOT, for example, requires a minimum vertical clearance for false work over freeways of 16 feet. So if you imagine a road that your final bridge only has about 16 foot 6 inch minimum vertical clearance, and if the minimum clearance for traffic over false work over traffic is 16 feet, and if you consider the depth of the false work itself about 3 feet, you can see how quickly you need to come up with a system that needs to accommodate this. So the temporary vertical clearance starts to govern your design. Caltrans has, the other requirement of building bridges on false work is that the final service limit state 3 tension at the bottom should be 0. So no tension is allowed in these box girder bridges in the final condition. And I think that's generally the practice, even if you build it on soffit. But I think especially when you don't have continuous support, like in the falsework system, you end up using the zero tension. Caltrans also has requirements of minimum vertical clearance over falsework, and they're slightly a little bit more relaxed in the sense of they only require 15 feet. And but they do have a caveat saying different things need to be considered while building these bridges on falsework, including the type of traffic. For example, if you have a lot of truck traffic, you may want to consider building your bridge slightly higher so that the trucks are allowed to move. And then the desire of local agencies come into play, as well as the cost of higher clearance versus the cost of traffic control plays into this. So when you build this type of structure, your main two criteria that you need to follow is that in case of either a widening or a new bridge, your proposed final vertical clearance needs to meet either the existing for a widening or a preset value like 16 foot 6 inches, which is the typical clearance over traffic. And then your proposed falsework vertical clearance also needs to be 16 feet. So this was one of the first bridges that was lowered in place, which is the US 60 Lindsay underpass. And as you can see, the existing structure was 6 foot 3 inch deep, and the widening was accomplished with a slightly shallower structure to meet the minimum vertical clearance, which was 15 feet. But with the falsework depth in consideration, you can see how they would not have met the 16-foot requirement. So this was essentially the first time a bridge was lowered in Arizona, and I just presented a quick schematic of how this is done. The blue represents the falsework, and the red represents the jacks that hold the bridge up in place, and the jacks are slowly released so that they come below to the final position. I have some more details of this in our case study, but I just wanted to show you a brief schematic of this. So what has been the history of lowering bridges? So I worked in Arizona for 18 years, so I kind of have seen this technology used from about 2004 through about 2024 now. The US 60 Lindsay, the previous slide I showed you was the first bridge that was lowered in place. It was 152 foot 6 inch span. The designer was URS. The second time that was done is also SR or by URS on the SR 101 90th Street, which was a design bid build project. And the third instance was the SR 202 McKellips Bridge as part of a design build, and PB was the original designer. And the final instance is the most recent one, which was the SR 101 Frank Lloyd Wright Boulevard, which was a design bid build and a value engineering proposal post bid award. And the designer, like I said, was WSP in Arizona. I just wanted to give you this information because I wanted to show that over the past 20-25 years, this technology has been successfully used and on different types of procurement methods, showing that it's both cost effective and a innovation in bridge engineering. The one with the asterisks is the design that I worked on, and I'll show you why I put an asterisk there. So I was the designer on these three bridges that are shown on the screen: the ramp east to north, and the two mainline 202 bridges over Southern Avenue. And I think we had designed this bridge as a lowering, the three bridges as lowering till about we submitted the 95%. And there was a property here that was on the southeast quadrant of the interchange that had not been acquired. And so we were not able to put a detour on Southern Avenue, and had to build these four bridges on falsework, with these three bridges being lowered. The fourth bridge had adequate vertical clearance. It was much higher than the remaining 3 bridges, that's the last bridge over here that is much higher than these 3 bridges. So that's why we had 3 bridges that are lowered and then the one that wasn't lowered. But as soon as we submitted the 95% submittal, we got an email saying that that property had been acquired. So we went back to kind of going back to the default of building these bridges on false work. And I think I was kind of sorely disappointed at that time because my whole idea of lowering the bridges didn't come to fruition. But my boss at that time said, well, you know, you might get another chance to do this. And so fast forward about 20 years, and I did get a chance to do it. So he was right. And this project is the SR 101 Frank Lloyd Wright. Oh, sorry, the SR 101. The project itself is from Princess Pima to Shea Boulevard. It's essentially a 5-mile general purpose lane widening. And like I said, the prime designer was WSP in Arizona. A good friend of mine, Chris Rodriguez, was the bridge lead. And all through the design, I think he and I had been kind of arguing back and forth about this bridge on Frank Lloyd Wright. And there was a debate of whether we should lower this in place or use the precast spliced construction method. And I guess during design, you know, I wasn't really involved in the design team, but they made the decision of going with the spliced girder option. The project was bid on November 17, 2023. FNF Construction, who is a local contractor that both Chris and I have worked with previously, they won the low bid at $108 million. And the bid specific, or this is the bid information specific to the Frank Lloyd Wright Boulevard Bridge, which had 4 beams precast, pre-stressed, spliced with a total of 8 webs and 32 post-tensioning ducts. They were spliced at 3 locations in the 220-foot span length. The final strength of concrete used was 8 KSI, which required a special mix design. And overall, the low bid cost of this, only the superstructure of this bridge, which is what we ended up replacing. So I'm just showing the superstructure cost. It was $3.2 million for both the northbound and southbound side. This was the typical section of the bridge. Once again, they have 2 beams side by side. So, and then you have the northbound and southbound side. There were 4 segments of the precast sections that are spliced into place. Now, if you looked at the actual beam section, it was 8 foot 8 inches wide at the bottom and 8 foot 6 inch deep. And if you kind of compare it with the dimensions of a typical truck trailer, it would kind of fill up the entire section of a truck. So I think there was some fear or consideration for transporting these beams unless they were like cast right by the site or something, or, you know, very close to the bridge location. The longitudinal profile of the girder is shown here. It comprises of 4 segments that are erected on false work and then spliced. So this is the original design still. So based on that cross section that I showed and the length of these segments, you ended up with pick weights of 90 to 125 tons, which would require a crane capacity of about 200 to 240 tons. But just to compare, the Texas 54 beam is the most often picked beam in Texas, and at 125 foot length, it only weighs 55 tons. So you can see that the weight difference, or the weight of each of the individual pieces, was quite a bit heavier than what is normally accepted. And the location of the bridge is also interesting. It's right by the Scottsdale Airport, and so when you have cranes or any erection uh, consideration, so this was the bridge location right here, and here you have the Scottsdale Airport, and if you have any obstruction in the way of the airport, you generally have to submit a FAA obstruction evaluation and the airport airspace analysis. And having done this in the past on another project, this is not a easy thing to get approval on, because and the other thing about the Scottsdale Airport, it's not a large commercial airport. It's more for private jet traffic. So to have 16 picks in this area with 90 to 125 tons was going to be a challenge. The other challenge was kind of the stage construction approach, where you had two beams side by side, and you had two stages of post tensioning. So the beams were supposed to be erected on the ground with stage 1 post tensioning, then placed on top of the false rock towers. Then you had to pour the diaphragms and the topping slab. And then you had to apply the stage 2 post tensioning. So the chance, if you have two beams side by side, the chance that they camber up the exact same amount is kind of, it's going to be a challenge. So that was another. And then the multiple stage construction required multiple closures as well. And once again, going back to the geography of this bridge, the bridge was here right by where it says Twin Peaks. And this is in a very heavily traveled area in Scottsdale, Arizona. So not only do you have the private jet traffic of the airport, you have EPC Scottsdale, so which is a golf course that holds the Phoenix Open every year, and with the Masters just recently concluded, I think golf is a big sport in Phoenix, and there's a lot of eyeballs on that tournament. There's also the Barrett-Jackson car auction, which is very close to the bridge site, and that brings in a lot of lot of car traffic, kind of elite cars and all that kind of stuff. The Westworld of Scottsdale, which is here, it also has many events throughout the year, including the City of Scottsdale Fair. And as you can see, there's a lot of residential communities in this area, as well as the big box stores like Walmart, Costco, Home Depot, everything that you can think of. And the other interesting thing here is that the City of Scottsdale has a lot of clout in this area, and ADOT wants to maintain that relationship pretty good, because I think the City of Scottsdale has a lot of, I guess it's financial clout as well as media savvy. So you don't want to kind of get on the bad side of the city there. So that was the kind of the context of the original bid design. As I said, there was a few or several challenges that needed to be overcome by the contractor team, including the pick weight. The precast form for the construction is a unique form. Transporting a 9x9 box that weighs 90 to 125 tons is not that simple. The camber between the two adjacent girders with the staged post-tensioning was a challenge, and the vicinity to the airport raised the picking challenges. The construction sequence that required multiple closures, and the multiple closures had to be coordinated with a pretty extensive event schedule that Scottsdale publishes every year. So like they have all these events that you can't have closures during these events. So getting multiple closures to work with those event schedules was going to be a challenge. Another restriction, because of these lengths of the beams themselves, there was restriction on where you can place the false work tower. So they may or may not have lined up with the exact lane configuration on Frank Lloyd Wright. And then the other kind of the bridge design challenges was requiring higher strength and the complicated detailing at the bearing, because this bridge also had a 3-foot elevation difference between the abutment 1 and abutment 2 side. So that was another challenge to face. What is a value engineering proposal. So what the contractor team did between November and January of 2024 was evaluate this bridge, and they decided to pursue a value engineering proposal. So it's basically a desire to change a construction method or piece of equipment. And the cost savings that are realized by a value engineering proposal is generally half the construction saving minus the design cost, and it's shared equally between the owner and the contractor. So the reason I put the design cost in red is that sometimes the owners tends to forget that they still need to pay the designer to do the design. So they generally think of the construction half times the construction saving as your amount of money that's out there, but it's actually you need to subtract the design cost. So in January of 2024, I got a call from Chris saying, hey, you were right, they should lower this bridge. And the first thing we did was establish the kind of the geometry of how this bridge was going to be lowered. The existing structure was a kind of an interesting twin cast in place box girder bridge, which on the northbound side was deeper by almost 1.5 feet, because it had originally been designed for overload traffic, and the southbound side was 9 foot 11 inches, and the profile of Frank Lloyd Wright was going down quite a bit, about 2 foot from the southbound side to the northbound side. So what we did was in talking with the contractor, we figured out what was going to be their falsework depth, and established that this southbound side had 13 foot 1 inch or 13.1 foot clearance under the falsework, and the northbound side had 15 foot 6 inch minimum clearance. Both of these did not meet the Arizona DOT's requirement of 16 feet. So the contractor decided to ask for a waiver on the northbound side because it was only 6 inches off from the criteria. So as part of the discussions with the VE proposal, they decided to so obviously the one big advantage of already having the contractor on board was we didn't have to guess what the falsework depth was going to be. So they had kind of already done some preliminary design on the falsework, so they were able to provide us with the exact the size of the beam that they were going to use that went over the traffic, as well as the so you have the wide flange 36 inch, and then you had about a 4x4 joist system that kind of goes between the steel and the concrete. And so we estimated the total falsework depth to be 3.5 foot. So we were able to pretty quickly establish what we needed for the lowering on the southbound side and the northbound side. So this is a kind of a synopsis of the schedule of the VE design. Even though the VE proposal was initiated in January, the Arizona DOT has a value engineering office, and they need to approve all the VEs. And I think there are certain thresholds that it has to meet. And so between January and April 1st, I think, of 2024, there was still discussion going on in the background. But due to our familiarity with FNF construction, and Chris and I had kind of had regular meetings with them, and we're kind of already orienting ourselves to be doing this design, but the actual design started in earnest on kind of April Fool's Day in 2024, and the decision about the two side and the one side lowering still had not been made. But the one advantage of this is that while the method of construction required lowering, the actual design of the bridge was agnostic to the method of construction. So we were able to proceed with the design and kind of submit like an early works package to the contractor for the post-tensioning as well as the typical section of the bridge. And then once the decision was made about the lowering, we were able to change some of the details at the abutment to accommodate the the lowering on the southbound side and not on the northbound side. And then we kind of finished the design sometime in August, and the contractor had about a month to digest the information that we provided them and start submitting the construction reviews that are required to go along with this type of construction. Uh, so the design of the structure itself it's kind of a simple span post tension box girder bridge. So it's not overly complicated. The the typical section previously had 18 foot 4 inches on the northbound side and the 19 foot 8 inches on the southbound side. And we were told that the abutments had already been, the abutment construction had already started. So our instruction was to keep the outline of the bridge, which is shown in green here. The outline of the bottom of the bridge had to remain the same. So at least we had a lot of our decisions were already kind of starting to be made. And so we were able to save one web. Like you see, the two boxes had two individual webs, but we combined them into one single web in the middle. So we reduced the dead load, but we also had one less web to put the post tensioning in. So, and the design of the post tensioning, we knew that the bid had used the 27.6 inch strand duct, and we were able to establish that we needed 4 ducts to be fit within the 9 foot 4 inches. So we came up with the eccentricity of the PT tendons at both the ends and the midspan, and we were able to proceed with the design. We used Bentley Conbox. It's a simple program. Once you get all the geometry set up, you kind of enter the values for the tendons, and you enter the eccentricity, and it reports like what is your jacking force required. And so in our case, the jacking force required was 14,204 kips. We provided 14,237. The initial strength required was about 4.5 KSI. We provided 5.5 KSI. The final strength required was 5 KSI, and we provided 7 because we wanted the BE design to rate slightly higher than the splice girder design. So, and the other reason was the camber. We wanted to control the camber on the widening. You don't want the camber of the widening to be, you don't want the widening structure to be higher than your existing saw cut elevation. So we worked with FNF pretty closely, and I think they surveyed the edge of deck at various points, at 10 points or 20th points, and gave us this information. So we were able to kind of get the bridge to work. And for the bridge geeks out there, I think there's like some fancy strut and tie modeling that needs to happen in the end zone, because you have very heavy pre-stressing force that needs to be transferred to the box itself. So this is the strut and tie model that I created. I'm not very fancy with the software, so I just kind of did it by hand. So and then you end up with specific requirements of rebar in the end zone. That's kind of summarized here, and that result, or we also have a strut and tie model for the top slab and the bottom slab, and that results in a pretty heavily reinforced or detailed sheet like this. And I know it looks kind of grainy, but I wanted to show you the amount of detail that gets packed into that one sheet. So I think this was a interesting sheet to put together. And as you can see, this is the southbound, this is the northbound. So there's not, as far as the lowering is concerned, there's not a lot of difference in the superstructure design. So where that makes a lot more difference is in the abutment. So to allow for the bridge to be built higher and lowered into place, we have to provide jacking pockets at the abutment, and the number of jacks is something that the contractor determines based on the dead load of the bridge. So this picture shows kind of the sequence of the lowering. So you essentially build the bridge higher first on false work, and then you remove the false work, and you have I have a better picture of this, but you essentially have wood wood members that hold the bridge in place when the jack is loaded up, and then you take out the wood pieces, and then you release the jack so that the bridge kind of descends about 6 inches at a time in each direction. So that's how the lowering is accomplished. The other thing that we were able to do with the cast in place construction is that we were able to take out the rotation out of the bridge, because if you imagine a precast bridge which has a 3-foot elevation difference between the abutment 1 and the abutment 2 side, the bottom of the precast girder also has to follow the same profile. But by using cast in place, we were able to level at the bottom of the abutment diaphragm. We had level both in the longitudinal and in the transverse direction. So this was done based on talking with F&F Construction, and this was their preferred method. But there are other methods that you can use. For example, if you think about the bridge being constructed on the top and the bearing below, you can also inject grout between the two members to build this. That's similar to what Saurav was showing, where you have the cast in place column at the bottom and the precast cap at the top. There is also alternative details that can be used like this. For example, where you can have the recess in the superstructure itself. This was done in the McKellips Road Bridge, but they had sloped web, so they were able to put the recess on the superstructure. But for Frank Lloyd Wright, we had vertical web, so this would have taken up the space that we had for the duct. So we decided not to use this method. And I think generally speaking, I don't like this idea, because you're introducing an opening in a very high stress area. So I think I personally prefer the jacking pockets in the abutment. So I'll kind of show you some of the construction submittals. The first one this is not for Frank Lloyd Wright itself, but this is the post tensioning duct submittal itself. It was for another. I didn't, for some reason, I don't have the post tensioning submittal on this bridge, so that's why I don't show that particular on this slide. But this is the typical submittal that comes in with the post tensioning, and the jacking submittal is the one that is key here, because in the unloaded position, the bridge is sitting on the wood beams, and then in the loaded position, you lift the bridge up to jacks, and then you take out the wood members, and then successively lower the bridge into the final position. So what happens is, whatever this distance was, you want to bring the bridge down to this elevation. So that's the goal. And this is a picture of the false work submittal itself, and it's essentially, like I said, a system of steel and wood members that is completely engineered by the contractor, and it does require some elaborate reviews. And I think with precast construction becoming more common, there's not a lot of people that have the knowledge or the expertise to even review these submittals. So I think that was part of being involved in this VE, was that I had some experience doing this in the past. And this was another interesting and unique detail for this particular bridge, where because of the 3-foot elevation difference on the bridge, we had to restrain the bridge on the lower end by putting these angles and with the wood beam, so that the bridge won't move due to there's a horizontal component to the gravity force due to the 3-foot elevation difference. And this is the final construction submittal, which is basically a winch system that allows them to remove the false work. So the synopsis of the VE design is that we lowered a 220-foot span cast in place post tension box girder bridge. It was by far the longest of the structures that has been lowered. The tight schedule required the design and the construction to happen in a approximate 6-month window. We needed to restrain the lower end of the bridge, and we got approval to do a single bound lowering versus the two sides. I think it was more of a detailing exercise. We had started showing both the details as being lowered, and then we had to kind of pivot halfway, so that just raised some additional detailing and CAD challenges. And I guess my whole takeaway from this is that we can still use old concepts even in the modern era. So, and then while we, generally for the VE, the owner and the contractor uh, don't share the actual cost information with the design engineer, but uh, I I have some friends in high places, I guess, and I was able to provide you some estimate of the cost of the savings, and it came out to be about $1,118,000, and I think roughly we had about $118,000 in the design fee. So a total savings for this bridge was about $1 million, which is not bad compared to the $3.2 million that was originally bid at. What are some of the advantages of having used the cast in place solution here is we didn't have to do the crane picks. We were able to use a nominal concrete mix design that was locally available. F&F Construction was able to self-perform the entire bridge. And then we didn't have the challenge of the adjacent beam camber or the multi-stage post-tensioning. It allowed us the flexibility to place the lanes lining up with the falsework system. The bearing design was kind of uncomplicated by making it level in both the directions. So we were able to obtain approval and lower only one side, and the other side was built on falsework. It was just not lowered. These are some of the pictures during construction. So as you can see, the northbound side, it's a typical lowering, so you don't have the jacking pockets. The southbound side has the jacking pockets, and you can see that the falsework has started to be constructed. This one is a view of the bridge, the top of the bridge itself. And here is where you can see the elevation difference between where the new deck is and the existing deck. So as you can see, this has to go down all the way to that elevation. There's also pictures of falsework itself. It's just to show like how elaborate the system is that you need to construct. And this is the final, final product. As you can see, the northbound bridge is quite a bit higher than the existing bridge. So this is where they were able to build this bridge in place without lowering. The southbound bridge is pretty close to the profile of the existing, so we had to build it higher and lower it into place. This is a video that I don't know if I may have to escape out of this. Oh, there it is. So this is a video of the lowering. And you have to watch carefully like how the wood shims are removed and the bridge gets lowered into place. So you see it? So finally, acknowledgements. Obviously, Chris, who was the bridge lead, and I've known him for a long time now, so he's a good friend of mine. Jackie Bradley at WSP, who did all the detailing. I'm pretty sure she was, there was challenging times for her, but she kind of smiled and did everything we asked her to do. Russ Stewart and Randy Simpson, who are good friends of mine as well. They were the first or the pioneers of this method of construction, and they did it in 2004 before technology was available. So when I first asked Randy how his lowering went, he said in the end it was all a big letdown. So that's where I got the title for the presentation. ADOT Construction, Joe Heller, who's at TY Lin, and I kind of feel old to say that I used to work with his dad, Dan Heller. So, and Greg Harasha, who is was the bridge PM or the bridge guy at FNF. I've also known him for a long time now, and he also has a PE, and he signs all the construction submittals himself. So he kind of puts his money where his mouth is. And he was very patient with, I made quite a few comments on his submittals, and he kind of grinned and bared it, and we were able to get this done pretty easily. Arizona DOT, they have the Flickr website, which is pretty interesting because that's where they share a lot of the construction photos and videos. They also have the road website, which shows like old bridges, the as-built, like when in Texas, it's very hard to find the as-built of an existing bridge, but in Arizona, that stuff is available online. Caltrans, they wrote the book on this type of construction, and there's a lot of their information that still comes in useful. Like they have a false work manual that shows how false work is constructed and removed. And some of the lessons learned that we went through during this project is that learning has no time limit. So I kind of felt that after 20 years I was able to lower a bridge that I had originally wanted to lower in 2004 or 5, and it's definitely it's easier to work with friends. So most of the folks here that I knew for a long time, and with the marvels of work sharing and technology, we're still able to collaborate and work across states. So that's a great thing that we have now. Be involved in everything that goes on around you. And sometimes, in these 4 months or whatever, I'm pretty sure I had some nights where I was like, maybe I should not have done this. But in the end, it's like discomfort leads to growth. The other thing is that complexity is not a goal. So I feel that making things simpler is a better option for the owner and the contractor as well. So and in this case, it was kind of proven, I think, with the type of construction that we use, and be flexible as things happen. We were initially we were told to lower both sides, and then they suddenly flipped it around and said, well, you because the other side was only 6 inches off, we want you to only lower one side. So we had a lot of changes that happened on our drawings and such, but we just kind of rolled with the punches. So that's kind of my presentation, and I wanted to thank Elaine for asking me to present here today, and Lucas and Jan, who then coordinated most of this effort. I know it takes a lot to put this stuff together, and I really appreciate all of you coming here today.